Dear students and budding engineers, I earlier presented some videos on design of spur gearing. Now I start with the fundamentals of machine design. You know that most of the machine components are subjected to loads which may vary in magnitude as well as in the direction. And such type of loading causes a failure of the component known as fatigue failure. Students in general feel a great difficulty in dealing with the problems subjected to fatigue loading. From the contents it can be seen that this lecture covers all aspects of fatigue design, starting from mechanism of fatigue failure, going through factors that affect fatigue strength of a material, then designing when the part is subjected to static and alternative stress cycles together. An illustrative example has been added for that. Then finally discusses design for finite life. Static or quasi-static, that is gradually applied loads, are rarely observed in machines. Parts of respecting machines, camshafts, shafts carrying gears, sprockets, pulleys and flywheels, gear teeth, belts, chains, wire ropes, springs, etc. are a few examples of parts subjected to cyclic or fluctuating loads, which we call as fatigue loads. Most of the failures and accidents encountered are due to cyclic or fluctuating and suddenly applied loads. Fatigue failure refers to the sudden separation of a part into two or more pieces as a result of fluctuating loads. Such failure occurs at stresses much lower than the yield stress of the ductile material and ultimate stress of brittle material. The failure takes place by the initiation and propagation of a crack, which is very difficult to detect, and therefore such failure occurs with little or no warning. Even in the ductile materials, the failure occurs without plastic deformation. Thus, understanding the phenomena of fatigue failure is a must for design of parts to have better dependability, life and performance. Here, the mechanism of fatigue failure is presented in brief. For greater details, the students can refer advanced texts on this topic. Several theories have been extended to explain the nature of fatigue. The explanation given here will help in understanding the phenomenon of fatigue and the effect of the various factors such as size, surface roughness, notches, alloying and heat treatment. Fatigue failure is the result of repetitive and quickly alternating elastic and plastic deformations. Usually cracks originate in grain fragments located on the surface stressed by tensile stress and weakened by stress results such as notches, surface roughness, etc. The zone of fatigue crack propagation has a dull but a smooth surface, while the zone of final fracture has a bright crystalline surface typical of brittle fractures as shown in figure 1. The crack originates at the surface and with passage of time it moves towards the core of the part as seen in figure 1. Since this propagation takes a long time, as the surface is smooth but a dull appearance is there. Finally, the part is significantly weakened and the fracture occurs suddenly. This surface appears bright because it is recent fracture of the part. We know that tensile test on universal testing machine is carried out to find the yield strength and ultimate strength of a material. Similarly, this fatigue test is carried out to find the endurance or fatigue strength of the material. This is known as standard rotating beam test. It is adequate for generalized fatigue data. In this test, a highly polished circular cross-section specimen is subjected to cyclic loading. Refer figure 2. In figure 2, the specimen is subjected to bending moment. As the beam rotates, the fibers of the surface of the specimen undergo reversal stress, maximum tension when at the bottom and maximum compression when at the top position. The stress time pattern is also shown in the figure. The tabulated fatigue strength values of the metals are results of this bending beam test. In the absence of specific information, the following approximate relations from test data can be used. Endurance strength in bending is 1 by 2 to 5 by 8 of ultimate strength for steels, and axial endurance strength of cast iron is 0.3 to 0.6 times of ultimate strength in tension for cast iron. Typical results of a fatigue test are plotted in figure 3 in the form of cyclic stress sigma versus the number of cycles n. With a decrease in the stress, it can be seen that the number of cycles necessary to cause fatigue failure increases. The ferrous metals and their alloys exhibit a knee in the curve. The ordinate of the horizontal part of this curve, shown as dashed line, is called the fatigue or endurance limit. It is the maximum completely reversed stress which these metals can sustain for an infinite number of cycles of loading without failure. However, the non-ferrous alloys do not exhibit flat part in the curve, and the curve continues to drop. Thus, there is no fatigue limit for such alloys. In order to characterize the fatigue response of both ferrous and non-ferrous materials, the term fatigue strength or endurance strength is used. It is the maximum completely reversed stress at which the failure will occur for the specified life, which is usually taken as 10⁷ load cycles. It is important to learn how to deal with variable or fluctuating loads for fatigue design. The fluctuating stresses on a part can be regarded as a combination of mean and alternating stresses. Figure 4a shows a typical realistic stress time pattern. In general, obtaining realistic data and their breakup in mean and alternating components is very difficult and is a challenging task. Stress time pattern shown in figure 4b is frequently encountered. Typical examples are helical and leaf springs. This will be more clear when we will deal with these topics. This stress in the figure is a combination of a mean stress sigma m and a completely reversed cycle stress sigma a. Their mathematical equations are given in the figure. This type of stress time pattern will be discussed in this video. There are many factors that affect fatigue strength of a machine component. They are listed here as type of loading, that is bending, axial or torsional, absolute dimensions of a part termed as the size effect, surface roughness and corrosion if any, grain size and direction, geometrical discontinuities such as holes, notches, fillets, etc., the heat treatment carried out, the residual stresses of fabrication or heat treatment, operating temperature, and type of cycle, that is degree of asymmetry, that is the combination of mean and alternating loads. A brief discussion of these factors follows. First, we consider how the type of loading effect is taken into account. In the case of bending, the fatigue crack initiates from the outer fiber where the stress is maximum. In case of axial loading, the entire cross section of the member experiences the maximum stress and the fatigue crack can start from anywhere. Thus, it can be expected that the fatigue strength for axial cyclic loads would be lower than the strength for bending. The relationship between the two has been found to be sigma En axial is equal to factor A multiplied by sigma En bending. The factor A is called the type of loading factor and its value lies in the range 0.7 to 1 for the axial loading. It is advisable to use A is equal to 0.7 in this type of loading in the absence of specific information. For cyclic torsional loading, the factor A is equal to 0.5 to 0.6. Hence, torsional endurance strength is given by 0.5 to 0.6 times of the endurance strength in bending. Now we shall discuss how the effect of the size is taken into account. The fatigue strength has been observed to decrease with the increase in the size of the machine part. With the increase in the size, the probability of increase in internal defects and heterogeneity increases because of greater volume. The probability of initiation of fatigue crack is increased because of increased surface area, and there is difficulty in obtaining uniform strength and heat treatment throughout the cross section of large parts. The effect of the size is taken into account by multiplying the endurance strength by a factor B known as size factor. For the value of size factor, refer figure 6 taken from reference 1. And it can be seen that the size factor decreases significantly as we move from size of around 10 mm to 200 mm. The fatigue strength strongly depends on the condition of the surface of the machine part. Rough machining, scaly surface due to hot rolling, and corrosion from water and acids badly affect the fatigue strength. The effect of surface condition on the fatigue strength is taken into account by multiplying the fatigue strength of the polished specimen by a surface correction factor C from figure 7. High strength materials are more sensitive to this effect, as can be seen from the figure. In the figure, the graphs are plotted for polished specimen for which size factor is practically 1, then the ground surface, machined or cold drawn surface, the scaly surface hot rolled or forged, corrosion of the surface of the specimen in fresh water, and corrosion of the surface of the specimen in sea water. And it can also be seen that the effect of the surface finish is quite significant, as the factor is as low as 0.15 for high strength materials when it is corroded in seawater. For normally used machine components which are machined or cold drawn, the factor lies from around 0.9 to 0.8 depending on the strength of the material. Now we discuss the effect of geometrical discontinuities and the stress concentration on the maximum stress induced in the machine part. In figure 8a, the plate is of uniform cross section throughout, hence the applied force F is uniformly distributed at any cross section of the plate. This has been shown by uniformly distributed force flow lines. The stress can be represented by number of force flow lines per unit width of the plate or by the spacing of the force flow lines. It is shown in the figure that the stress induced is the force F divided by the area of cross section of the plate, that is Wt. In figure 8b, the plate width with hole of diameter d has been increased to W plus d so that the net area of cross section at section AA is the same as in figure 8a. For the same force F, the stress sigma based on the net area must be F divided by Wt as in the first case. But the stress sigma dash in the region close to the hole has been found to be higher than the stress sigma. Refer figure 8c. The force flow lines pass round the hole and are crowded locally, causing a rise in the stress. Thus the fibers close to the hole are subjected to increased tensile stress due to crowding of the force flow lines along with the bending stress due to the bend in the force flow lines. Refer figure 8b. We considered the effect of any geometric discontinuity on the stress induced at the geometric discontinuity. Now we define a factor, stress concentration factor, the ratio of the maximum stress sigma dash at the section with geometric discontinuity termed as stress razor to the average stress sigma at the section based on the net cross-sectional area is called the theoretical stress concentration factor Kt. Thus, Kt is equal to maximum stress sigma dash at the geometric discontinuity divided by the nominal stress sigma. Factor Kt is a function of the geometry only. For values of Kt, any handbook or textbook on machine design such as reference 1 and reference 2 may be consulted. Static or gradually applied loads. In ductile metals which are subjected to static or gradually applied loads, the yielding takes place at the points of excessive stress, and this reduces the intensity of the maximum stress. As a result, the effective stress concentration factor is lower than the theoretical value Kt. In brittle metals, there is no yielding and full value of Kt must be considered. Now we consider what happens in case of fatigue loading. The weakening effect of stress concentration becomes more significant under cyclic loading. The actual stress concentration factor in fatigue, called the fatigue stress concentration factor Kf, depends not only the type of stress razor and the material of the part, but also on the nature of the load cycle. The relation between Kf and Kt is expressed as Kf is equal to 1 plus Q Kt minus 1, where Q is a measure of sensitivity of the material to the discontinuities. However, it is very difficult to specify general values of no sensitivity index Q because it depends on the chemical composition of the material, the heat treatment given, and the nature of cycle. The values of the no sensitivity index Q in table 1 may be considered in the absence of specific information. The students are advised to refer the handbooks of machine design. For cast irons, the strength reduction due to stress razors is very low. This is because of the fact that internal stress razors, that is the flaky inclusion of the graphite, has already caused a significant reduction in strength. Hence, the effect of external stress razors may be neglected. For grey cast iron, the value of this factor is 0 to 0.2 as given in the table. If there is any doubt, use Q is equal to 0.2. There is a scatter of the fatigue life data, and the curve on the sigma n plot represents the mean of these data as depicted in figure 3 earlier. Hence, the design of a part based on the tabulated values of the endurance strength of the materials would be only 50% reliable. Table 2 gives value of reliability factor R to be considered in the design equation based on the desired reliability or survival rate. From table 2 it can be seen that for 95% reliability, the fatigue strength must be reduced by about 14% because the factor R is 0.864. But as we go for higher reliability, then the factor reduces significantly, and at the highest reliability in the table, the strength is to be reduced by about 40%. Considering all the above discussed factors, except the stress concentration factor, the fatigue strength for the design is defined as design endurance strength sigma En design is equal to ABCR multiplied by sigma En bending. Similarly, the design stress for the axial and torsional conditions may be defined. It is to note that all these factors A, B, C and R are having value unity or less than unity. The factors which we have discussed, if they affect the fatigue strength adversely, the factors A, B, C and R will have values less than 1. The discussion on fundamentals of fatigue design will continue in part 2, where an illustrative example has been given to make you understand what we have discussed in this lecture. For greater details, please refer the references given here. I hope you have liked the lecture. Please feel free to send your questions at my email address given on the first page. Please wait for part 2 of this lecture. Thanks.